Welcome to today's webinar on monitoring and evaluation. Thanks already to all the speakers and participants of this webinar, and special thanks to the Riga Energy Agency who organized this webinar series. Today we will be talking about the topic of infrastructure and utilities. And this is the last and final webinar of this webinar series. My name is Benno. I work and I'm coordinating the overall project of which this webinar series is a part of. And just as look at the next steps, we will have another webinar in February, which will be dealing again with the topics of our project Smart City and the impacts of COVID-19 on smart cities. And we will be announcing this webinar online, and we'll also let you know about any updates in the future. Yeah, thank you. And I wish us all very fruitful discussions. I hand over now to today's moderator, Frank, and who will be going in more detail. Thank you.
Thank you, Benio, and welcome also from my side. Not from Riga, but at least with a virtual background. We would love to be with you. As I see here, it's always, the sun always shines in Riga. As Benno said, our last webinar for this series, and as in the previous ones, we have good speakers. We have a lot of possibilities for you to ask questions and to give us your feedback through some polls. And please use the chat functions if you have questions or comments in between whenever you have them. And we will, of course, before we start, try the poll function. But first of all, let's have a look on the agenda of today. The next slide. Today, as Benno mentioned, it's about the infrastructure and utilities, and we have 5 cases from Riga and from Vilnius about drinking water, energy blocks, air quality, energy consumption, and stormwater management. And all the speakers are already in the house, in the panel, so we are ready to start. Before we do so, let's kick off with the first short poll on our participants of today. Who's with us? Which sector are you from? And while this is running, I would hand over to give us a little intro to today and a little welcome note from the city of Riga and Riga Energy Agency. Christoph Kaugers will be the one of co-hosting this webinar today. And I can see from the first poll results, majority comes from public municipalities, which is good. This is exactly where we're talking about, mainly infrastructures and utilities in the hands of the public domain, mainly. And a quarter comes from academia. Okay, so I hand over to Christoph.
Hi, hello everyone. As I was introduced, my name is Christoph Kaugers. I represent Riga Energy Agency here, and I'm honored to open this the last installation in these in this first round of 3x3 or 4x3 sets of short conversations, talks on these topics, and I just want to start with reminding us all that our pre-assumption is that you can change only things that you can measure. And judging by this, we have gone through in the Riga series through governance, transportation, and now it comes to infrastructure and utilities. We sometimes think that only the top layers can do the decisions based on smart city installations. But then, as all of these seminars have proved us that you can make impacting decisions on the whole scale, starting from city governance, going through businesses, and also on individual citizens' case. And I think today we are on the opposite end of that scale. We are coming to utilities, to the smart meters, to installations that we face and love and have used to enjoy on an everyday basis. And we only think that most of those things and decisions lie to us, people, citizen, and in our behavioral change. But sometimes it is challenge as well to change the back up the ladder, the governance decisions. So by saying this, I welcome all of our speakers today who will cover such topics as water, rainwater, energy positivity, smart meters and what we can do with them, and much more similar questions. And please, I will end here.
Thank you, Christoph. And we will prepare for our first speaker. And today it's so that we will ask questions to the audience before each of the presentations, and the presenters will have the chance already right away to react and maybe touch upon the results of your feedback. So the first presentation will be about drinking water, fresh insights gained from a new drinking water quality monitoring technology. And the first question to you is, do you actually drink tap water? And then we'll have a follow-up question. I can see that majority is positive about this. And while we wait here, I introduced already the first speaker. I announced already the title. He's from the Riga Technical University, Sandis Dejus. And yeah, 3/3 of us are drinking tap water. And the follow-up question would be, if you don't drink, why? Or if you do, what are the most common reasons not to drink tap water? So there's a variety of topics, and you have multiple choice possibilities here. We'll give you a moment. It's a bit to read. I have a tap water in the meantime. So it's all over the place, the results. We'll see in a minute. But interestingly, the majority goes to the taste, actually, of tap water, and then followed by filtering, exposed to other issues in the water, and chlorination, and not wanted to use recycled water. Okay, so does this surprise you, or have you expected something different? We will hear about it from Sandis, please.
So thank you for the introduction, and it was nice to hear that most of you actually drink the tap water, since it's super safe in our region, and it's a very good choice to do that because it's environmental friendly, and it's also your wallet friendly, since it costs like it's 300 times less than the bottled water. And in terms of this presentation, I'm going to give you a brief insight in the possibilities, what to do in the water sector in terms of the smart cities, and what actually we can do and monitor in the water supply systems, and maybe show some benefits that we can acquire during the monitoring process in the real scale systems. And as it was introduced, I am Sandis Deis, the senior researcher in Riga Technical University, and I work in the laboratory of water technologies and biotechnology. And we have done quite a lot of research in terms of drinking water quality and monitoring of that in terms of at least 10 years. So I'm going to show a couple of our ideas, results, and possibilities where to apply also our systems in the water supply networks. But overall, to give you a brief introduction in water supply, the biggest challenges in water supply systems, in centralized water supply systems all over the world, is urbanization, because it leads, and climate change. And in terms of urbanization, the guess is that in terms of 30 years, the cities will grow by at least 66%. It means that the water supply networks will extend, or they will be needed to extend. And for example, in terms of today, Riga water supply network is longer than 1,500 kilometers, and it grows. And if we look at the bigger size cities, those million cities in the world, so the networks are much bigger, and the biggest issues is to sustain the quality of the water in such a kind of networks, because it takes quite a while to travel from the drinking water treatment plant till the consumer. For example, in Riga, it might be even 4 days somewhere. In bigger cities, the time can be much longer. And the other factor or challenge is the climate change that causes the trouble with the water sources, because there is water source depletion found in a lot of countries in the world. Luckily, in Latvia or in Northern Europe, we are quite happy that we are using less than 10% of the water sources that we have. So we are not we do not have so bad impact in terms of that. However, we should also think in scale of the whole world to make some good decisions and also some scientific findings. And the challenge what we need to face that the water sources are depleting, and also the networks are extended, and we still need to sustain the amount of the water which must be supplied to the customers, the quality of the water that is supplied, and also it should be supplied within some reasonable pricing. It should not cost very much. So we need to find some balance in between of those three, let's say, parameters. And yeah, in a lot of cases, it can be done, or it is done more or less manually in water supply systems, and the systems can be improved by installing some devices or additional monitoring equipment. As Christoph said, that we cannot do or understand anything if we don't know the data actually. So we need to monitor the systems, and the water supply system monitoring can be divided in two parts. It can be done regards the hydraulics of the system, meaning that we can measure the flows or other hydraulic parameters, and on other hand, we can measure the quality of the water. Can we sustain the quality all the time, or is it safe or not? And in terms of the quality, we can monitor the parameters as pressure, as flow, in most of the cases, and by monitoring those parameters, we can actually understand does the system work properly, and find some troubles with that. For example, we can find the leakages by doing some proper monitoring of the systems. And in terms of the water quality, we can actually say water is safe or not, or it can be used as a drinking water or not. Now, luckily, as I said, in Riga, we can use it safely, and it is not a trouble, and it doesn't cause any danger to your health. And to improve the systems and improve the everyday maintenance of the systems, we can do the online monitoring for both, for hydraulics and for the water quality, and gain a lot of good things actually, or benefits. And for example, if we do the hydraulic monitoring, we can, as I said, find the leakages. For example, the average leakage rate in the water supply systems in the world is about 20%. So we can imagine if 100 cubic meters is pumped to the network, so about 20 cubic meters is lost somewhere in the pipelines, in the holes of the pipes. So quite a lot of water can be saved. On the other hand, we can also maintain the pressure in the system if we monitor the pressure actually. In that way, we can save some money on the pumping energy that we put to the water. And yeah, if we monitor the quality of the water, we can increase the safety, and in that way we can raise the loyalty of the customers, that actually they believe on the water utility. And that is one of the most important issues that actually we face in this region, that the customers quite often doesn't believe to the companies that supplies the water, and therefore drink the bottled water instead of tap water. So we need to raise this total belief in the water utility. So it's very important to show that the water is safe and high quality. And what we do in the Riga Technical University, we are developing the systems that monitor the drinking water quality. And in everyday situation, the water comes from the river or underground resources. It's treated and pumped to the city, and everyone is happy. Unfortunately, there happens different things in the water supply systems time to time. Some problem in the water source or water treatment procedure, or maybe some corrosion is happening in the pipelines, or some bacterial regrowth, and the customers are not happy and complaining. And in most of the cases that are the most dangerous, the impact is caused by some bacteria or microorganisms. For example, in the Northern Europe, in 2007 in Nokia, there was 9,500 people get sick from the bad quality water in the city because of the failure at the wastewater treatment plant, where the wastewater actually was pumped into the water supply system. And for example, in Östersund in 2010, it was 27,000 people who got sick after some microbial intrusion into the water supply system. Therefore, our main scope is to develop some system that can monitor the microbial water quality. And we have developed such a solution in our labs so far, that we can actually measure the microbial quality of the water in terms of 20 minutes. And if we compare to some other methods that is used day by day in water utilities, we can save, let's say, at least 18 hours, because methods that are used in laboratories takes at least 18 hours to get the results, because a lot of technological stuff that is done in the labs. But we can do it in 20 minutes, so we can get the answer regards the water safety much faster. And if we put it in the scale of Riga city, for example, we have done some modeling, and in a case of some interruption of water supply system by microbial intrusion, by applying of existing monitoring, at least it's just a case, not a case, the example. about 10% of the customers might feel some impact from this case. But if we introduce our new approach, then only 1% of the customers will feel something bad or not so good about the water. So we can reduce the territory or the number of the customers that is complaining on the water quality at least from 2 to 50 times, depending on the place where the incident has happened. So by installing online drinking water quality systems, the customer happiness level might be raised significantly, and moreover, the loyalty to water utilities can be raised. However, we have also tried to introduce some approaches to the water utilities at the moment, and they are not very ready to implement such technologies because of the high costs of them. And not only on the quality, but also hydraulic monitoring systems. But hydraulic systems actually can give a lot of benefit in a long term in a saving of electricity and water. So the awareness of or knowledge of the water utilities should be raised in a long scale. A huge issue is how to bring the data from the underground to the ground level, because the water systems are beneath the ground. So we are facing this kind of issue at the moment. And it's not only in Latvia, it's all over the world. Experienced labor is needed to run those systems, which is a big trouble also in most of the Europe, because the water sector is one of the oldest, in meanings that the employees are very old, and therefore new systems are not taken in practice very fast. And the systems also should be tested still and tried in a real scale. And to implement such a systems, it's required to get a long-term planning, and not only in the water utilities, but also in the scale of municipalities, to make some priorities and to find some investments in such a systems, because in most of the cases, the water utilities cannot invest in such a systems because it cannot be paid by the everyday like expenses from the water utilities, which are limited by the tariff legislation. So the water monitoring or the water supply system monitoring is like a next step for our water utilities in the Baltic State region. In Western world, it's happening more or less somewhere, but still, regards like the water quality monitoring, there's only some examples in the world who are actually doing the online monitoring on everyday basis. So we have to face still a lot of challenges to implement such a technologies in the world. And more or less that's all. And as I said, I am happy to hear that you are drinking the tap water. And regards your concerns on the heavy metals, I can wash away your fears, because we don't have any heavy metals in the tap in Latvia. And also the water cannot taste like a chlorine in Latvia, because we don't chlorinate the water. And luckily no one was afraid of the cancer, because it's also not a trouble in Latvia regards the drinking water, because we do not use the chlorine, which might be cancerogenic in some cases. Yeah, so I hope that I didn't fear you, and you will still drink the tap water, because it's safe and clear in all over the Latvia. Thank you.
Thank you very much, Sandis. And there's actually a follow-up question to what you just said. If it's the water is safe, you of course take care of the pipes up to a certain point where it's handed over to the house utilities or multi-apartment utilities. So what to answer to the question from one participant, not sure about the quality inside the multi-apartment building?
Okay, that's one of the most typical questions that we have. Of course, the water utilities regards the Latvian legislation is responsible for the water quality till the building. And in terms of the internal network, the responsibility lays on the shoulders of the owners or the company, the maintenance company, or how it's called in English. And the water utility day by day does the quality measures. For example, in Riga city, it's at least 40 places where daily is taken the samples and analyzed. And the samples are taken from the internal networks, it means from the tap, not from the street somewhere. And the samples and the quality of them are showing, or the results are showing that in like 99% of the cases, the water quality is good enough and better even than it's posted in the regulations.
Mhm.
And to avoid a bad feeling, let's say, or taste of the water when you drink from the tap, we are giving some tips, let's say. One of the tips is to flush the first couple of seconds the water in the tap to reach the cold water temperature, 8 to 12 degrees, and it's going to be fresh and safe. And sometimes it tastes strange because of some microorganisms that can be grown into the water, but we should not be afraid of that. It will not affect our health since we have full stomach of the microorganisms. It's like billions of them, and it just makes the water taste a little worse, let's say, but it will not affect your health, even if it's tastes bad, maybe.
Mhm. Okay, thank you very much. You mentioned already you unfortunately have to leave earlier, so you will not be in the discussion later on. So a short follow-up question actually on what Benno mentioned. We will look onto the effects of COVID-19 to smart city developments. Have you monitored a difference in water usage over the time or over the different measures taken where people stayed or were staying more at home or mobility was decreasing? Was there any effects?
Yeah, we did kind of research in Latvian water utilities. In European scale, it was quite a big changes because big factories were stopped, and therefore the consumption, not the balance, but division between the industrial usage and people usage was switched. In case of Latvia, it was not so obvious because the big factories still were running mostly.
Mm-hmm.
But when the people moved, it was seen that the water consumption in the domestic areas rised, and also rise the number of complaints in those areas because the velocity in the pipes rised, and maybe some brown water, as it's called, came to the buildings.
Mm-hmm.
But it was only a couple of cases like that.
Okay.
But mostly in Latvia, it didn't change. In Western Europe, there was a huge changes in the water networks.
Okay. Thank you very much for your contribution. And yeah, we would move on to our second topic. Before we hand over to Andra Brunberger from the Riga Technical University, we have also again 2 questions to the audience. So the next topic is about positive energy blocks in the case historic urban environment from Riga. And the question for you, first of all, is, has your city implemented positive energy blocks? If you're not aware of this term, it's about a grouping of neighboring connected buildings which are producing, also using this own energy. And so we'll see that. I see that the second question is also up already. What are the main challenges of implementing positive energy blocks in existing urban environments, cost, technology, or legislation? And I can see that we'll have to, it's good that we have this dialogue here. There's not too much known about positive energy blocks. Looking at the result of the first question, it will be shown in a minute. And about the main challenges, it's quite spread over legislation, followed by cost and technology. So, Andra, the floor is yours.
Yeah.
Please explain your case. Thank you.
Yes. Okay. Sorry. Now some technical issues.
That looks good.
Yeah, I just have to move this tab over here. Okay. Yeah. Hello. My name is Andra Blumberga, and I work as a professor at Riga Technical University Institute of Energy of Environment and Energy Systems. And yes, and today I will tell about positive energy block in historic urban environment, and will use Riga as a case study. About the definition, what is positive energy block, or in short, we call it PEB. There are four main criteria. First of all, it should consist of several buildings. So they should be new, retrofitted, or a combination of both. It should have an annual positive energy balance, and this is where the word positive comes from. The buildings have to actively manage their energy consumption and energy flow between buildings and then wider energy system. So basically, it's use of waste energy, and they should make optimal use of elements and a list of different technologies, including different advanced materials, IT technologies, energy production technologies, and so on. When we started the project, actually we had this kind of internal discussion among ourselves, my colleague being an architect and me being an environmental engineer, how to maintain a high quality Baukultur, which is basically defined by Davos Declaration, maybe more known to architects, and global climate change, which is mainly represented by Paris Agreement. So how to have a sustainable building stock, which is not damaged by different energy efficiency and renewable energy technologies. So, this is where the beginning of the project lies. And we had, when we started the project, we had to decide which block in Riga city center we will use as a case study. So the first year of the project we spent on different criteria for selection of the block from this historic center. And what is a tricky part here is that the whole city center, historic city center in Riga, is UNESCO protected. So it's a kind of heavy burden on all these buildings that are within this city center. So so mainly it was energy perspective against cultural heritage and livability perspective. The first year ended, and we selected the block. Those who are from Riga can recognize probably the block. It's the block. It's usually called Palladium Concert Hall block, and it has different shops, small offices, residential buildings, catering, big offices, and entertainment within the block. It has historic buildings in green color, Soviet time building, and there are even two spaces for nearly zero energy buildings that will be built, I believe, quite soon. And we have to study applicability of different energy efficiency measures, waste heat options, and renewable energy sources used within this block. Within this study that I show, it's the second year of the project, we built a model to study how to reduce impact on climate change, at the same time regenerate urban environment. So what did we do? We built from the scratch a model. We use a system dynamics approach. It's hourly energy balance, and we have decided to look on three different scenarios. First is energy efficiency renewables first, The second scenario is architectural values first. And the last one is kind of compromise between these two things, energy efficiency, renewables, and architectural values. Here you can see different technologies from the energy supply side mainly, but we look on the energy reduction as well. So we first reduce energy consumption, and then we reduce it either in PV modules, in PVT modules. We use heat pumps, we store heat, we use district heating, electricity grid. And I will give you some insights in the model. The modeling approach we use has a beautiful features that we can make a user-friendly interface on the top of complicated mathematical models. And here I will show you. First slide is about heat consumption in buildings. All these letters on the x-axis represents different buildings. So each building is one letter. And what I did, I just started the simulation, annual energy consumption for heating. You can see the consumption, annual consumption without any energy efficiency measures, which is basically now, has 4.6 gigawatt hours a year. And then what I can do, I can run the simulation again. And anyone else who goes in the model can do the same. I run the simulation, and this means that this scenario is how to reduce heating energy consumption within the block and in each building separately. And you can see that the number has decreased. Then I will just switch this off. Then we can look on the waste heat as well, and there are continuous waste heat sources and intermittent waste heat sources in this block. So we can see on hourly basis how the waste heat is accumulated over 1 year period. And then we can look even more closer to heating side, and this is just an example again. So what I will run now, this is how the heating is supplied now today for this block. So what we can see here, that we basically have a supply dominated by a supply from district heating network. And here we can see on the top, we can see different heating sources as well. We can see that it's mainly dominated by the different district heating temperatures. But then what we can do, and what you have to look now, how the graphs are changing, that we will reduce energy consumption, and the graphs will change. Now you see that the consumption has decreased, and now I will install renewable sources, different renewable sources. We have to wait a minute while the model calculates, and we can see that I will just switch this off. That without any subsidies, without any subsidies, we can see that PVT panels produce provide some heating energy. Heat pumps that are mainly working on a PV electricity produced by PV, and then and there is no heat storage within the block. But then if we increase the subsidies, so we have to provide some subsidies for heating. So we see here that then the district heating is small, and we can have a heat pumps producing most of the heat needed for the block. And we use seasonal heating storage within the block as well. So if we just to take a very quick look on electricity part, again we see different producers of electricity. Here we can see today we have only mainly grid, but then we can again reduce consumption, and we can install renewables. And now we will see how the picture will change. That now we have a PV and PVT panels generating electricity. Something is taken from grid, something is sold to grid. So we can play with different scenarios and different alternatives. So this is very quick overview of what we can do. We can do many more other things as well. So conclusions for now, this model is still work in progress. But the conclusions that we can draw out from it now is that it's technically feasible to reduce energy consumption by two different scenarios. You can see the percentage. Subsidies are needed for both energy saving scenarios. It's technically feasible to reach positive energy block for both heating and electricity production, and we can use seasonal thermal energy storage in the block. Subsidies are needed for heat pumps, heat storage, and PVTs to be economically feasible. And what is important, how are we going to do our further research, is we will go more deep by applying this tool to behavior of inhabitants. So we will do research on social acceptance. In January, we will start to develop single player and multiplayer games, and we will kind of create a hypothetical positive energy block. And we will study how inhabitants might behave within a positive energy block. Yeah, and the research is funded by Ministry of Economics, of state-financed project. Thank you very much.
Thank you very much, Andra, for introducing us to the energy block, positive energy block example from Riga. What happens after this this project ended? Do you have requests already from other similar locations in the city, or is there still something to be developed in the system, because you use existing technologies in the end? So what would be the next steps to implement?
Actually, when we started, we had this kind of like a very academic exercise. Without even idea, making it, it's kind of become like a real. But what has happened so far is that it really seems that it might become real, because this project generates the next ideas and next ideas. So we have applied for new funding because people usually say, yeah, but come on, it's like a historic urban environment. But what about multifamilies building outside the historic city center? So we have applied for a project for this kind of in the Soviet time buildings to see whether we can do it or not in that kind of environment as well.
Yeah. So in the end, the owners have to decide upon the subsidy investing or getting subsidies to being able to build this infrastructure, and you will continue to kind of support this with other cases and other locations. And you mentioned also, please.
Yeah, because the ministry is the one who is financing this research project. So after 1 year, we have to make a kind of guidelines and recommendations for the government about energy communities. What have we found out, whether they are feasible or not, what kind of support do they need? Yes, so that's another outcome from the project.
And besides such guidelines, you mentioned in your conclusion that you are aiming for some gamification also to introduce it to the inhabitants, so that they kind of get interested and get used to it, or what would be your expectation from the inhabitant side?
Yeah, so because we don't have such an energy community or positive energy block, like a real one, where we can kind of interview inhabitants, so we will create kind of hypothetical positive energy block or energy community, where these people kind of, by playing a multiplayer game, they will kind of live within this block and make decisions whether they go for the PV panels on the roof, or they go for PV panels on the facades. They do internal insulation, external insulation. Do they store energy within the block, within the building? Yeah, so they will play, and we will register their decisions by computer. Computer can register every single decision made within the game. So, and then our partners from they do sociological research, so they will draw out some conclusions how people behave within this kind of blocks.
Okay, yeah, very interesting. There was actually a question coming in to the chat. Could you show what happened when you choose the architectural button?
It's just I can do it if we have the time. Do we have time enough
Yeah,
to do this?
give it a minute, no
Yeah.
problem.
So I can, while it's running, I can give a quick explanation what the difference is. Yeah, so remember this is 2.79, and then if I quick simulate this. So basically the difference is that for energy efficiency first means that we do a maximum of technical solutions for energy efficiency. Kind of the biggest difference is that we do insulation of building envelope almost the whole surface, while for architectural solutions we do only from the yard side, backyard side. So we do not touch any surface that is kind of, let's say, protected, or architects would like to protect these things. So this goes to windows and other things as well. So that's the main difference. But this number comes from each building separately, and it's summed up in this slide.
Okay, I think this is very well answered. Thank you. Good. Are you with us later on?
Yeah, I'm sorry, I have to leave because I have a big webinar going in parallel.
Okay.
So I have to go back.
So good that we answered this right away. And thanks again for your presentation.
Yeah, thanks for inviting.
Sure. We'll move on to the next topic, which is about air quality. From measuring instruments to publishing data, work experience in Riga City Council. And we have Evita Vitula and Janis Kleperis here from the Riga City Council, Department of Housing and Environmental Board. Before we do so, before we hand over, we have again 2 questions for you in regard to this next topic. What is the greatest source of air pollution in your city? Multiple choice. And do you trust your city to report proper air quality results? So while we wait for the results, Janis, is it you to speak, or Evita? Who's?
Okay, hello everybody. Just I am involved in Riga City Monitoring Group in 1998 and still is managing monitoring equipment. Evita is much more acquired in air quality topics, different, connected to everything with city, because good air quality is quite important. And responsible for the air quality in Latvia is State Ministry of Environment and Regional. And they are also doing monitoring on the background, but Riga City is doing is okay, there are results.
Yeah, there are the results. Okay, it's a mix of the sources, some others which are not further explained, but salt and sand and industry, the majority, and somewhat or positive to trust in quality reporting. Thank you. And so I would say you will start your presentation, and your colleague Evita is taking over, or is it only you?
Only I.
Okay, okay.
She is busy with another duties just now.
Okay, no problem. So please.
Okay, I already started with the short introduction. Now about air quality and public health. As it's shown by World Health Organization, there are quite important air quality because they, from very much research, compiled pollution sources and dedicated concentrations, and it's on the base on the Clean Air Directive of European Community, and also it's elaborated in the guidelines of our Ministry of Environment regulation on air quality. As we see, Latvia is quite comparable regarding particulate matter pollution with Europe average countries. But regarding nitrogen dioxide, we are a little bit cleaner. But what is air? When we are looking in the engineering toolbox, the air mostly contains oxygen, nitrogen, argon, carbon dioxide, neon, helium, krypton, hydrogen, xenon. And I want to ask you firstly, in this row, do you see some polluting substance? Please show the third question.
I will ask Benno if he has prepared this question, which
if no, then I ask.
Yeah, there it is.
Just wait a little bit, because there is one important matter in this list which is responsible for climate changes. And is it also a polluter or no? What was the meaning of this question? How you are thinking?
Mm-hmm.
Not so easy to decide, I see.
Yeah, a lot of different pollutants listed. And
they are not really pollutants.
No.
They are only consist in the air.
But 70% or more, about 70% says yes.
Yeah, it's not the right answer, because CO2, this is quite important only in climate changes, but the sources of CO2 also are humans. Everybody who live body is the source of CO2 pollution, and we all are involved in this recycle of CO2, also vegetables and so on, because the answer no should be correct. Why? Okay, I will close this pollution. And next, please. Could you help to...
You have to switch the slides.
Switch the slides. Okay, yeah. Here we saw some polluters. They are CO2, nitrogen dioxide, ozone, carbon monoxide, but it's quite different from carbon dioxide, benzene, and particles. Their concentrations are too low because they were not shown in this previous table. And those polluters are in all guidelines about clean air. There are different technologies to measure air pollution, and Riga city already from 1994 are using so-called differential optical absorption spectroscopy, open light beam spectroscopy. It includes in real-time measurement, quite large area of air. For example, our stations have light beams 300 and more meters, and the pollution is measured in this matter based on Beer-Lambert law of absorption molecules, pollutant molecules in the air. Why this system works? It is the light source, then it is open light bars and light receiver, and then monochromator and computer who is calculating measured values. Because air turbulence and winds and so on, it's not so easy to measure, and there is a special light modulator which helps to measure 3000 spectra per minute, and from those spectra are calculated different spectral regions for specific molecules. As we see in this table, there are different polluters and also different wavelengths, and it is possible to make measurements of 6 gases in 3 minutes for all spectral regions. And what we are doing, the next is mathematics. There is a written reference spectrum of clean air, and then the measured values are divided with this reference spectrum and averaged, and every 10-minute data are stored in wireless data servers from which we are calculating different time values of pollutants. Air quality in Riga is measured by a number of monitoring stations, and there are involved state, municipality, and also enterprises in Riga's free port mostly, because they must measure particles and also benzene pollution if the works what they are doing increases special limits, for example, 1 million tons of liquids or something more. Background pollution is measured by the state, those green monitoring stations. But there are 3 stations of Riga City Council. This is on region where the port is quite close. It is seen here. This is the enterprises of Riga City Free Port, and there is a light source on the top of shop. This is a light source, and there is a receiver 310 meters in distance, and the wind from those directions blows the pollution if it is in the light beam, and it is shown by measurements. One more station is on Brivība Street, but the light beam is 2 times 340 meters, because it's a little bit newer station and it is using the same receiver and light emitter in one device, and it is reflected from special mirror, like in the next station. Mirror is such, looks like this. It needs no electricity power. And previous street station is measuring the traffic pollution, and also what we are measuring, it's a pollution in household region of Riga city. It's in Pardogova situated, and also the light beam is 2 times 170 meters. Where these data are used? It's firstly, I will show 2 examples. It's firstly used for online presentation, like as a quality index. Here is the right link to those data. And what we see here, it's 3 stations, port, it's a traffic station, and it's household region in Riga. Just now we are seeking here in this example. Yesterday I made photos, screenshots from those household region station. This station, it's quite good air quality. Here we see which pollutants we are measuring here, PM2 and 5. It's quite stable concentrations because it's average 24-hour value for PM2 particles. It's no 1-hour values like in next graphs for nitrogen dioxide. We can see some activities in the morning hours and also in evening hours. There is a the contour street where private cars are going quite frequently. Sulfur dioxide is coming from boilers, and as we've seen, it's a little bit cold, but the values are not too high, and also ozone is on how values it's measured and showed. Here how air quality index is divided in 7. Just recently it was only 6 parts, but now it's 7 parts, because in this autumn we had some episodes with fireworks in Russia and Ukraine, Belarus, and also the impact on the air quality in Riga. Okay, the next application, every year we are making annual reports on air quality in Riga. I will show you a couple. They are available in our homepage of Housing and Environment Department in Riga City Council homepage. You can download those values. Here is data presentation from 2019 years. This in July, some episodes of benzene pollution, benzene. And here are collected measurements for more than 10 years, only annual average values of nitrogen dioxide in 2 background stations. Those data are obtained with the same equipment as Riga City Council is using, but with state. Okay, it's shortly all what I wanted to tell you today.
Thank you very much, Janis, for taking us into the air quality monitoring. There was a follow-up question. You explained that there is some online presentation of the different stations, but there were shown 3 stations, but there are much more in Riga. Are the others also available online, or is it just certain reasons for this?
Others not belongs to Riga, but are available are results from state Latvian Environment, Geological and Hydrometeo Agency. They are on their web page. The online results also are shown, also like in the way of index. But equipment from monitoring of air quality in Freeport from enterprises, they are not available for online.
Okay, so it depends on the source of.
Yes, that's right.
And I would have another question. Is there a certain decision making? You said that you report to the state every year, but if during the summer, for example, certain measures going beyond the thresholds, is a kind of a warning system that they should start to think of rearranging traffic or arranging the heating in the winter. So is there a clear link to certain decision making?
Yeah, but it's not so dangerous was for Riga to involve the information. This is also the main task what is doing state monitoring stations, because it's the transborder pollution, and the cause was not in Riga. But we are using also our measurement data for different another tasks. For example, to make action program for Riga City to improve air quality. Such programs 3 are made in Riga. It's 5-year programs with different actions. What different departments of Riga City Council are doing and what impacts the air quality on the best, and to receive starting position what we have in Riga, we need on those many year air quality measurements. For the forecasting air quality, here I show is Riga Air Text. It's also our Riga City Council is participating in the doing. And it's organized by Cambridge environment specialists together with Riga City One environment specialist group. And they are showing forecasts for 3 days. And when the air quality is coming to be best, it's due to meteorological weather or some border pollution. Also, it shows that you can take some measurements if you have some accidents.
Yeah. Okay, so forecasting is what
Yes.
drive the decisions. Okay. Thank you very much. Looking in the chat, no, there's no other comments or question at the moment. Thanks again for sharing this. And we come to the fourth topic. It's about the smart meters. Anna Mutule from the Riga Technical University will present electric consumption assessment using smart meter data and KPI methodology. But before we do so, again, a question to the audience. How smart is your home? Do you use any of the following devices? Please make your choice. And Anna, if you like, you could already start your presentation. Anna is from the Faculty of Electrical and Environmental Engineering, the Institute of Energetics. And we'll wait a moment for the results. Looks like that about half of the participants use one or the other device, and the other half, none of the above. So there's potential to increase, and maybe we learn something how to do so. Anna, please.
Very interesting results. Because when this workshop organizers asked me to provide a question for this session, my question was much more simpler. I just wanted to ask, do you have a smart meter in your house or apartments? And there are just 3 simple answers: yes, no, or I don't know. Then yes, we received very interesting results, and I'm really, how to say, surprised that people are aware about different kind of technologies. Of course, it will be very interesting to see the regions, but I believe that almost all let's say, general public in Latvia already know what is it smart meters, because the programs of the smart meter rollout program will be finalized in the next year, and actually all the consumers will be installed with the smart meters. Yes, thank you. First of all, good afternoon, all the participants, and my name is Anna Mutula. Thank you for introducing me. Maybe I would like to say that yes, I am a part of the Riga Technical University, and I'm associate professor there, and I'm just lecturing, but regarding the research and this particular research which I will present today, I am doing this in the Institute of Physical Energetics. This is a state research institute on the energy field, and I'm a head of Smart Grid Research Center. And yes, the topic of my presentation will be about the smart meters and its deployment actually around the world. And for the introduction, I just want to say that what I will talk today, everything is based or been created under the project, an ICT platform for sustainable energy ecosystem and smart cities. And the project is already finalized, and it was realized under the project program ERANET, Latin American countries. So I had a unique opportunity to collaborate with Latin American countries, and I was a coordinator of the project, and it really was very exciting to go this 3 years way, you know. And we had a We had 7 partners from 5 countries, and the IP was the coordinator of the project, and we had also the partner from Brazil, Institute for System and Computer Engineering, and we had 3 partners from Chile, 3 universities, and actually we had, let's say, like a mixture of different kind of expertise, and our Chilean colleagues, they're experts on the communication technologies, and we also had Polytechnic University of Bucharest from Romania, and they are also from like a power sector as we. And actually the partner from the INESC Brazil, it was they are specialists in computer technologies, and particularly in the application developments. And we had another one partner just joining our project for 1 year, the company which which is located in Barbados, and actually setting up PV solar panels in Barbados. So here for just some, this is for introduction, but if we are starting from the let's say from the beginning, I was really surprised that actually all the countries, not only European countries, has the same priorities, the same main priorities in the energy field, and they are like energy efficiency, they are behavior change, they are energy consumer becoming prosumers, and renewable energy sources based energy, and reducing energy consumption, and developing also some tailored innovative solutions and services for the consumers. So taking into account these all things, I'm not going to present all of them during today, but I would like to present you some a very small part of the result achieved during this project, and the main, how to say, proposed was to create key performance indicators for the project goals and to measure. And you know that this approach is widely used now everywhere in the projects, and let's say everything what can be measured and what can be evaluated, and in different directions. So we choose this one, but to be able to implement a KPI evaluation, we need to have a, let's say, the instrument, a tool, and we decided that the main tool will be a smart meter, smart electricity meter, and actually for our research we use the real smart meter measurement, like a week consumption samples to compare accuracy of the model, and we use yearly consumption as a target for the modeling file in consumer, and we use the consumption modeling results to simulate the actual consumption based on available information. So we set up some KPIs for our project, and then we were very lucky to conduct this study based on the pilot implementation. In the framework of the project, we set up 5 pilot in UPB in Romania, in the UPB campus dorms, and you can see now on the picture these 5 pretty, let's say, old buildings, Soviet Union buildings, and in each of the 5 dorms we set up smart meters, and this deployment contains 39 smart low cost average meters, shortly SLAM, these smart meters were developed under the Nobel Grid. This is a Horizon project. They actually had a very nice goal to create, let's say, low-cost smart meter, because all of you know that is very expensive for the moment. And also these all dorms were equipped with 12 smart meters, with the 3-phase smart meters, and which give us possibility to compare results, to get more, to get maybe even more data. Sometimes when we didn't get data from one smart meter, so we can combine it somehow, we can cover with the different data from another smart meter. And as you can see on the slides, during this study, a series of issues were also identified in this campus. And yeah, some may be not explained, and sudden increase of the energy consumption, and possibly this cryptocurrency mining, and also some, let's say, difference between the total bill and the consumption from the smart meter. Due to some internal reasons, 4 of the 5 aforementioned dorms are used, actually were used for the modeling purpose. The general overview of the dorms is collected in the table, and you can see it right now. The information includes number of floors, approximate number of inhabitants, living space size, estimated share of the renewable energy, the available area of the roof, and yearly energy consumption received from the smart meters. And the yearly energy consumption information is taken from the smart meters, and you can see it here, the curves. And what is for us, it was very important, even if you use the smart meter, so it means that you can see just the curve. You don't know what is going on under this curve, yes, and if you don't know this information, you can't, let's say, change your behavior, you can't change something, and you need to have more information. Of course, in case if you have like a smart house or maybe smart socket, you can collect maybe more precise information, but this is what we had here. And the idea was to understand what is behind of this curve and how we can change and how we can maybe, let's say, decrease this consumption, maybe to give some tips for the students to change their consumption. Regarding the let's say, some other data, this campus is actually, they are working on to create this, to transform this campus into a smart city living club. And this solar panels is already installed on the faculty building, and it means that they already have a lot of results. They have already some information on the solar, from the solar panels. Yes, so to understand the behavior of the consumers, we, under the project framework, we developed, let's say, consumption survey, and it was conducted to access the appliance list and their use habits, providing a view on the potential consumption in cases when no consumption metering equipment is used. The survey covers 24 hours interval for big days and weekends with a specific 15 minutes intervals. And in the figure, you can see a sample of the conducted survey table. There are 2 main axes also. You can see the horizontal axis represent a time step, and the vertical axis representing the list of the appliances, as well as their assumed average nominal power. And we ask each person in these dorms to fill in this survey. and the person filling out the consumption survey use the numbers from 1 to whatever, I mean, there is no limits, and representing the number of the certain appliances used in an exact time period. And by using a number larger than 1, user can show multiple similar type appliances used, or if or greater appliances nominal power, the average specification. And each survey was individually analyzed to create potential day-to-day changes in individual situation. So the next, I would like to say also about the additional information we created under this project. So this is needed to optimally indicate the local situation in Bucharest, where the dorms are located. And there are 2 types of information, actually, 2 types of information, local natural lighting, in order to simulate natural lighting situation, and solar generation. As I said before, they already had some kind of installations of the PV solar panels, but in this case, the information was provided from the location near Mania. So model development was the most difficult part of this project, and actually I'm not going in very details because this model consists of the different small models, and I will give insights, a little bit insights of the some of the parts of this model and the very important user behavior model. And this model creates a necessary reference for user daily activity. This reference includes sleep period, outdoor and home activity. Activity label with outside is referred to any activity the user is engaged in outside of his living space, or on the other hand, activity labels with home indicates user availability at home and the potential contribution to the overall consumption. One of the, actually altogether, we have created 48 user behavior models. This is just an example. And one of the 84 collected student schedules were used for each user, providing study occupation for every work day of the school year. And additionally, time up to 1 hour of the study schedule start and the end. Additional time interval is added, simulating travel time, longer classes, or early arrivals. The next one is the daylight model, also was very important for our dorms, for our study. Is used to organize the data collected from the online weather source, using only the daily light portion of the information. Daylight is used as an alternative lighting solution for artificial lighting, actually for the modeling process and for the giving some tips to the final results. Then another one important model, which is the appliance model. The individual user consumption creation is based on the all appliances used by the user. All appliances used by the students user have been assessed and modeled individually. So we received results from the 24 appliances in total. The appliance also unique from one to another, share similar operation and control basis due to the performed survey time step scale limitation. The appliance model used 2 operation time periods, morning and evening. They are shown on the figure with the example, just an example of one case presented. There are two operation areas in concrete for some appliances that require user interaction, such as the TV, PC, but can also be flexible for appliances that require user interaction but operate beyond the area, such as the washing machine, phone charger, and so on. The control setting of each individual appliance is made unique based on 11 parameters. And this is, let's say, the main mapping models, but of course, I'm not covering everything, maybe the most, how to say, understandable for the moment. And going to the results, we can go, like, say, like back to the smart meters. And actually what is most important is to have this curve, and then we using our models in different combinations and special algorithms. So we fill in the received smart meter curve. And then of course, the validation actually based on the comparison between the received results from the modeling and real consumption. And the data analysis covers the approaches used in the developed algorithms to test the achieved model result accuracy, and algorithms used to approaches peak comparison and direct value consumption. And each approach examines data differently, but both the data sectoring. So you can see here that we use two kind of this is a visualization of the peak consumption approach and deep and peak consumption. Let's say we divided by 96 sectors here and compared with the real results. And also here we use some kind of shaving of peaks and draw on dips. And then we received results. So here is the real consumption. Here is the model consumption. You can see, okay, we still have some, let's say, difference, but and the achieving accuracy was estimated is around like 80%, 80%, which we think that it's really good result for us. And what to say, going back to the KPI list, we investigated for our project 3 categories of the KPIs, and we were able to calculate say energy use, like a very technical KPIs, and green energy, the possible use of renewable energy sources, and also carbon emission reduction. And what is very interesting is that we decided to include the part of user awareness here. And it's really, this possibility gave us these surveys which we conducted during the project. And to the results, to increase the share of green energy, theoretical implementation of PV panels on the available roof space of each dorm and additional energy storage system is used. Main limitation of this assessment, excess generation from PV cannot be fed back into the grid, and energy storage system is only charged by the PV panel excess energy. Each dorm has 2 types of setup estimated. The first type you can see in the table, it's a PV panel generation at dorm's peak consumption. And second type, it's where energy storage capacity dorm's peak kept the dorm's peak consumption. And here you can see that the consumption reduces by, in the first case of the PV panel, by 48%. And if we install additional storage, so we can get like a 58% of the consumption reduced. And regarding the user awareness, in this slide, we have some examples of appliances that could be impacted by the user awareness. And the impact is estimated from 0 to 100% with the step of the 5%. From the results, which is highlighted 0, 50% and 100. This is done to address the original consumption the appliance produce, which is the 0%, and the potentially reachable reduction to lower amount, which is the 50%, and maximum reduction to lower amount, which is about 100%, but we think that is more theoretical. And 5 examples are given in the figure. So the first one column is a natural lighting use over the fluorescent lighting. And the second column is conversion from the fluorescent lighting to LED lighting. The third column covers the use of sleep mode of PC. And fourth column explored the potential of PC use reduction by up to 20%. And the last column, similar to the previous PC reduction, the TV reduction operates on similar principles as the PC reduction, but let's say not fully used in a sleep mode. And in the table, you can see when, for example, with the 50% user awareness, through PC sleep mode utilization, dorm consumption is reduced by 2.1% from 28.1 to 26.0. And the KPI results.
Would you come to an end after the slide?
Excuse me?
Would you, we have to look at the time a little bit. Would you come to an end after this slide?
Yeah, this is the last slide.
Okay, so, very good.
This is the last slide, and yeah, I'm just what to maybe to highlight here is that yeah, for instance, the increased share of the renewable energy sources was just in a let's say analytical, it's like was a feasibility study, and we received a very good result, which can be used as a base for the further evaluation. Thank you very much. And of course, I let's say didn't have a lot of time to go in deep in details, but we have a project web page, and there you can find all the executive summaries for all deliverables, and also the concept of application development. And if you are interested in any results, please contact me and I will share with you all the results. Thank you very much for the...
Thank you very much, Anna, for this overview on all these findings of your project. There is one question actually from Kristaps about the future of on-demand electricity models. How would you say, what are the biggest challenges to make this mainstream?
Just a minute, I'm trying how to say to...
Yeah.
I will stop to share my screen and then maybe I... Okay. Can you please repeat your question?
I was asking of what would you say are the biggest challenges to come to a more on-demand electricity model?
What is the biggest challenge? You know, this is very philosophical question, because you know, we have a lot of different kind of models, and everything what can help to us is to get a very precise information. And actually, during this project, we collected, we have a lot of databases with particular appliances, so we can, how to say, we can use the information, and not only from Latvia, but also from Romania, Brazil, Chile, and it's the biggest challenge is information, let's say.
Okay, thank you. There are no more comments at the moment. I would say we move on to our last but not least topic. It's about stormwater management, and we're moving from Riga to Vilnius now. And before we start, and I introduce Egidius Stinovacius, the head of marketing and communication of the municipal company Grinda from Vilnius. And here are two questions for the audience. Does your city suffer from flash floods? And what is the main cause of those? While we are waiting, maybe you would like to share already your screen and start the presentation. The presentation.
Oh, hi, hello everybody. It's been a pleasure. Very interesting presentations, and I'm afraid I won't be able to share anything as close to what we've already seen. But how much time do we have?
15 minutes.
15 minutes is what we need.
Yeah. So I guess we will have the results confirmed now. You can see them.
Oh yes, it's yeah, quite a common problem.
Exactly.
And well, I'm also very interested to see that this repair of drainage systems is one of the main reasons for the cause, as a main cause of flash floods. Mm-hmm. Interesting. So let us see how we live in sunny Vilnius, and whether the insights that participants of this webinar are comparable to our insights. Okay. So let us start. Well, who we are, the company Grinda was founded some time ago. It is obviously fully owned by the Vilnius City Municipality, and we are a relatively small company in terms of turnover, but we are the primary contractor in providing city services in the city of Vilnius, and we have many different fields of activities. 18 we count, but collection and management of the surface runoff or the stormwater is one of the largest our fields of activities. Well, where is Vilnius? Vilnius is on the east side of the Baltic Sea, just a little bit south of Latvia. And funny historical fact is that Vilnius stopped a glacier some 16,000 years ago. And this is where the Vilnius city was founded. The glacier obviously formed big hills around the city and formed huge prehistorical rivers. River Neris is as wide as nowadays Amazon River. And because of this difficult terrain, we have huge altitude drops between the top of the hill and the river. So it's approximately 140 meters. That is very much comparable to the size of a TV tower. Another funny fact is that Vilnius is actually rainier than London. The climate in Vilnius is humid continental, meaning semi-marine, semi-continental, which means we have a lot of precipitation, a lot of rain. Winters tend to be quite harsh. Summers might become pleasantly warm. On the average, we have 125 days of precipitation, and the average precipitation is approximately 680 millimeters per year. What we notice that in the last couple of years, the extremities, the climate extremities have become harsher, and the amount of precipitation that we have is increasing. Well, and I made a little calculation, amount per precipitation per day. When you compare the amount of days and the precipitation, means approximately 8 millimeters per day. And the days of precipitation obviously are from the very pleasant drizzle to real downpour. The fun fact is when it rains, it pours, which means that a lot of water flushes down the hills into the central city area, thus flooding some streets and causing massive problems. You would obviously ask what is the situation with the infrastructure? In the modern times, meaning the post-19th century Vilnius, Vilnius had several big waves of infrastructure development, one starting with the Polish occupation, when the central city area was rapidly urbanized, and from what used to be the village type of a city, it became a proper city as we know it. Back in those times, they were built the mixed type sewage system, as you can see it in the lower left corner. Vilnius actually is quite famous for its yellow brick structure. Another big wave was the Soviet times. It was the rapid expansion and building new micro districts in the neighborhoods, and this is when the most part of the dedicated rainwater sewage system was built. And during the independence times, I must admit that we have neglected the rainwater systems, although the city was developing quite intensively and extensively. And nowadays we are maintaining the existing systems mostly. But having said that, this means that we need to put a lot of effort in fixing the city planners' mistakes. And the circumstances that we have are quite difficult. The weather extremities, as I mentioned before, intensify, meaning that we have more days with quite heavy rain, and the rainfall itself becomes much heavier. Probably you have noticed that in your countries respectively as well. Also, we need to take into consideration that the city area is growing, and the amount of hard surfaces, meaning the parking lots, the buildings, the streets, and so on, increasing every day. The buildings alone constitute 20% of the total city area, and that's quite a lot, which means that more rainwater cannot be absorbed into soil, and all that amount of water, the increasing amount of water because of the heavier rainfall, has to go into the drainage system. And since the drainage system is overloaded, then we have problems. Unfortunately, we are fighting the consequences rather than the causes of the problem. And each year we have 4 to 6 massive scale flood alerts in July and August when it is hot and when the weather extremities become really obvious. What we have done so far, we have allocated teams which come into the 7 to 6 risky areas and divert traffic from places which can be flooded. And after the rain and after the flood, we clean the debris that is brought down the huge hills. As I mentioned to you before, Vilnius is basically in a huge basin or a big sink when everything that comes in has to go out through a quite narrow piping. And the choices are really tough. First option that we have is to relieve the strain, meaning that we need to reduce the amount of water coming into pipeline, and we have that possibility, and I will tell you more about it in a few minutes. Another alternative is increase the capacity, or in other words, make my logger bigger, meaning that we need to repair the existing systems and build larger diameter drainage systems, and also improve the elements that are already in the system. Each of those solutions have their own pros and cons. Nowadays we think more about the relieving strain from the existing pipework because of the ecological situation and environmental issues. Because if we do not flush the water into the river immediately. It stays on the surface and gradually and is gradually absorbed into the soil, which means that it retains the irrigation system of the rivers and creeks and so on and so on. What we have started doing is, so we're building accumulation ponds, and these ponds become the green oases, which retain water and increase the ability to develop different ecosystems. These green oases can be adopted for recreation, which is not something very unusual throughout the world, or in Vilnius for that matter. But still, for some city planners, it's a challenge, which can be overcome. And as for the increasing capacity, since we have, as I mentioned to you before, 4 to 6 full-scale floods throughout the year, it would be extremely extravagant to build huge piping that would accommodate all that water that will only be used 1 to 2, well, 1 to 2 weeks per year. So we need to find a solution somewhere in between. The truth always lies somewhere in between. And as for sustainable stormwater management, we definitely looking into the four issues, meaning that we need to think about the water quantity and replenishing the rivers and the creeks. We also need to look into the water quality, and this is why we're building the water treatment plants, local treatment plants on many outlets. Then we obviously think about the recreation value and biodiversity. And the best practices for the accumulative basins or accumulative ponds are found in numerous places around the world. This is the Alewife Reservation Stormwater Wetland, that's in Cambridge, Massachusetts. On the photo above, you can see it filled, and on the photo in the bottom right, you can see it nearly empty. There are multiple examples of such practice, including one in Vilnius, that is Ozopakas, and the water is collected from the nearby buildings' roofs and is diverted into the pond, which once again looks quite nice. In 2017, we're in Vilnius, started a huge regional project that is supposed to help with management of the surface wastewater systems. We're rebuilding or reconstructing 7 different sites in six different locations, and we're also make the inventory of Vilnius City rainwater networks. The project is funded by the EU, partly funded by the EU, partly by the Vilnius City municipality. Why it is important to account the inventory? Well, we have nearly 100 stormwater output points throughout the river. Here you can find the link to the interactive map, and for time saving sake, I will not go into that more deeper, but you might find this interesting. With this project, we're inventorying some 1,500 kilometers of the piping, large diameter piping, and that eventually will allow us to create a hydraulic and hydrological model of our piping system, which in its own account will allow a much more accurate system capacity assessment. So whenever there is a new real estate developer comes into the Vilnius City municipality saying, we want to build a new building over on the Shishkina mountain. We might look into the hydrological model assessment and say, in order to collect the rainwater, you need to do this and that, and it will be only a very small part that of the water that we will be able to feed into the existing system. Several other things that we've done. Karoliniškės water treatment plant that collects the water from several living districts. That was built back in 1985, and back then it was very, very small. The city was under the beginning of the rapid development. And nowadays, these areas are fully populated, and by our estimate, some 100,000 of residents live in those areas where the water comes into this water treatment plant. Once again, please note, there is a link that you might find interesting, and you might watch it at your leisure time. With this water treatment plant, we built a huge accumulating storage pond that helps preventing floods to the nearby villages. And obviously the water is being treated and cleaned from the petroleum products and sand products. Well, I want to present to you two case studies. One is Geležinio Vilko Street project, and obviously it is much more complex than we will be able to see in here. But for those of you who have been to Vilnius, you probably would notice that Vilnius starts on the hills some 11, 12 kilometers from the river, and unfortunately the stormwater system has not been built to accommodate all the water that comes from the newly developed areas. By our calculation, the water flow is about 30 cubic meters per second, and no system is able to cope with such amount of water. So with this project, we're going to redistribute the rainwater flow, and part of it will be diverted into the rainwater storage facility, meaning accumulated pond. The water will be obviously pre-treated. Storage volume will reach some 20,000 cubic meters, and from that pond, the discharge debit is only 1 cubic meter per second, which is already the proper amount that the systems can cope with. And this is the picture of the accumulative pond. This is how it would look like. This is how the architects see it. This is the pretty much full pond, and this is how it might look when it's empty. Obviously, the greenery here plays a substantial role. It would either finish cleaning the remaining products or the residues, and will obviously help to recover the ecosystems, meaning the fish, the frogs, and other small fauna, and birds as well. Case study number 2 is a Narbuto Street project, and this, I must say, with some pride that this is the first municipal project in Lithuania to be done with digital information building, with a building information methodology, which allows to proper plan and execute the project in different phases, shorten the implementation time, save resources, and it's also very, very useful for the later exploitation of the project. So here we are. On the right side, you see an excerpt of the map. This is where the Narbuto Street is, and you can obviously see that it is located in the center of Vilnius. It is an important junction with 4 big living districts, and the stormwater networks that were built back in 1966 cannot cope with the amount of water coming from all those districts, because everything eventually flows downhill and onto the river. When preparing the project and when executing the project, we found that the piping, the drainage pipe was, first of all, of course, is of insufficient capacity, 800 millimeters diameter at all. It was also damaged in many places. In some instances, it had a negative slope, meaning that the water, instead of flowing down the hill, was reverted back. And since it was built in the late 20th century, obviously doesn't meet the nowadays environmental requirements. This is the part which can show you the project in more detail. From top picture, you can see the most problematic part of the street. It's marked in red. In the middle, you can see the altitude changes of the terrain, and that also presented us with some problems. The street itself is highly traffic intensive, and the altitude leverage was also something that we had to take into account. And the solution that we chose was doing the micro tunneling method, meaning that we buried the old pipe that was insufficient and damaged, and instead we built a parallel new backbone pipeline, which had twice as big diameter, which means that the capacity increased mainly 4 times. Since the project was so big, it also contained some other pipeline, side pipelining, diverting into the backbone. And we also built the water treatment plant near the river. Once again, there is a shortcut to the video you'll be able to see. And the water treatment plant, we built a French technology. It has suspended solid particles. This separation chamber, and also petroleum product separation chamber, and automatic shut off valves, and so on and so on. And as you can see, it's right in the middle of the city, right next to the huge office buildings. And that presented us with some problems. Once again, you'll be able to see some videos, how it's done afterwards. This is actually the picture here depicts how it is done, how this place looks nowadays when it's all done. In the bottom right corner, where my mouse is, you can see a little landing. This is where the big modern water treatment plant facility is buried. So the main takeaway from this project is, well, that can be done. Well, what you need to do is plan accordingly and be open-minded, and even in the heavy traffic streets, you can do that. What we've done, we use the green zone separating two traffic directions, and the micro tunnel was going down right in the middle, and that did not. This allowed us not to shut off the traffic completely, and in some 12 months time, we're done with this project. So that's that. Well, if you have any questions, I'm here to answer you.
Thank you very much, Egidius, for your presentation and the cases you worked on, the projects. Looking at the chat, there's no immediate question now. I would actually have one. Is it
On you go.
besides the environmental effects and besides the safety and management issue for the stormwaters, is the groundwater an issue in Vilnius? At least here it is. The groundwater levels are too low, and we have to make sure that enough water precipitates down, infiltrates down again.
Vilnius is in a very good location in this sense, and Lithuania overall, because we have several layers of groundwater. One is that is directed into in the form of springs and creeks that flows into the river, whereas we have, and that's some 8 meters or so deep, the first level, and under the ground, some 30 to 70 meters deep, we have huge potential of the potable water.
Mm-hmm. Okay.
So it is not that bad. As a matter of fact, the water is in Vilnius is that of a very good quality.
Mm-hmm. That's good to know. Okay, thank you very much. Well, we are running through a lot of important and interesting infrastructure fields here today, so we are a bit out of time with all the 5 cases and presentations. I would, to wrap up, ask our participants if this was worth listening, this was helpful for you today, a final poll for you. And I would then also hand over to Christoph if he has some final remarks as our co-host of today. Here comes a final poll for you. And as said, this is the last webinar of this dialogue series. We will have one extra in February, and we will approach you. We're inviting you and looking forward to continue this beginning of next year. And thank you for your feedback, which is again very positive, I can see already. And Christoph, would you take over here?
Impressive.
Christoph, please unmute yourself.
Okay, so I was apparently muted for all of this time.
Any final comments and remarks to close today's webinar?
Yeah, sure. So I wanted to finalize this with just turning back to this remark that you can change only things that you can measure, and I think we can safely say that today we found out that even the most rigid systems like utilities and utility systems can become smart and adapt and change. So, and I think that the fluid systems like people and their adaptations should be changed or should be adapted more easily. But it's also something that we learned today that it's not always the case and can be quite challenging. So us, the people using the new possibilities, and also the decision makers and the governance part of the decision can also be rather stubborn, and changing this trend can be tough at times, tough at times. But just using the chance, I would like to say thank you to my colleagues, Eva and Nika, who helped or actually worked the hardest to create all of this. So thanks for their. Thank you everyone else as well who participated, because I think we in these seminars we have had surprisingly large participation. So thank you everyone who's joining in, and hopefully I think Frank will probably share this all of the information will be available later on, and we will be happy to answer any questions or other extra questions that you might have. I know that I have some, and I will address those to people separately. Thank you, everyone.
Thank you. Of course, presentations and recording will be made available, documentation to the webinar on our balticsmartcity.com webpage. Thank you, everybody. Have a nice afternoon and stay health, safety, and in good mood. Bye-bye.
Thanks a lot.
Bye. Thank you all.
Right, bye-bye.